Welcome to the presentation. Today, we will discuss some of the phenomena and experiments in our daily lives, and we are going to attempt to explain them using physics concepts. Today, we will be looking into two concepts, torque and forces. Have you ever wondered why it is a lot easier to open the door when the handle is further away from the hinges instead of opening it near the hinges? Before we dive into the explanation, take a look at this video as a demonstration. In this video, I tried to open the door by gripping the end of the handle. Now, what happens if I try to open the door by gripping the handle near the hinge? In case it wasn't clear, I felt a significant amount of resistance and I had to apply more force than before to open the door. Hence, there was a short delay in the video when I realized that I could not open the door with the same amount of force as before. We can actually simplify the model of the doorknob into the diagram shown below. The hinge of the doorknob can be represented as the pivot. The distance between the position of the hand and the pivot is denoted by R, meaning that the perpendicular distance of the line of action of the force is given by R sine theta. Recall that torque is equal to the product between the force F and the perpendicular distance of the line of action of the force to the pivot D. In this case, D is R sine theta. Since the weight of the door remains the same, the sum of anti-clockwise moments remains the same. When D increases, less force is required to produce the same rotational effect. Similarly, when D decreases, more force will be required to produce the same moment about the pivot. Another application of torque can be seen when children are having fun at the playground. Two people may have different masses, but using the principle of moments, whereby the sum of clockwise moments equals to the sum of anti-clockwise moments. The lighter person can sit further away from the pivot compared to the heavier person to create a greater moment, lifting the heavier person upwards. Here is another example of how torque is demonstrated. Credits to SUTD for the video clip.
Okay, walk up to the wall.
Yes.
And then heel toe, heel toe. That's it. One more time. And now translate over, but don't come in or out. Okay. Now bend over the wall. Bend over. Put your head on the wall. Pick the chair up. Now stand up.
Ha.
That's fair enough. Don't hurt yourself.
Yeah. No, there is actually no way.
Okay. Toes against the wall. 1, 2. Okay, now translate over. Now you might be able to do it because your feet are proportionately small. Okay, down.
Well,
Pick it up. Pick up the chair first. Clean pickup of the chair, please. All right, now stand up. Okay, come on over. Bend over. Okay.
So why can the woman in the video lift the chair but men cannot? This is because typically men are taller than women and hence the center of mass of men is higher than that of women. The center of mass of man is beyond his foot. Using the right hand grip rule, the thumb represents the direction of the torque. The rest of the fingers represent the direction of force. The normal force exerted by the man from his foot results in a direction of torque pointing out of the page. The man rotates counterclockwise. Consequently, if the man exerts more force, he will rotate harder into the wall. Hence, the man cannot stand up. On the other hand, the center of mass of woman is about her foot. Using the right hand grip rule, the normal force exerted by the woman from her foot results in a direction of torque pointing into the page. The woman rotates clockwise. Consequently, the woman can exert sufficient force and rotate away from the wall. Hence, the woman can stand up.
Did you know that something as unassuming as air resistance can surprisingly be a lifesaver? Even though you may not have parachuted before, it is understood that without the parachute, a fall from such a height will cause fatal injuries. So, what exactly is the reason behind the importance of having a parachute, and how does it relate to the concept of air resistance? Let's watch this short video to have a better idea about how air resistance plays an important role in the act of parachuting.
Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity, right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she's stopped falling, it means she's stopped accelerating. She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachute opens, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea. As she hits the ground, there's a thumping great counterforce from the earth, which decelerates her very quickly.
To summarize the video, when the person jumps out of the plane, the weight of the person outweighs the initial air resistance, causing her to accelerate downwards. The speed of the falling person increases, causing more air particles to collide with her at every second. Over time, the air resistance increases until its magnitude is equal against the weight of the person. This in turn slows her down before letting her fall with terminal velocity. After opening the parachute, the huge surface of the parachute causes a massive amount of air particles to collide with it, increasing air resistance significantly. The speed of the person decreases as the air resistance outweighs the person's weight at this point in time. As her speed decreases, the air resistance decreases until it is equivalent in magnitude with her weight. You might be wondering whether you can investigate the phenomenon of air resistance at home. Of course you can. The following video demonstrates the effects of air resistance on a piece of cloth when it is folded and when it is unfolded. This is the data collected from the short experiment. In the experiment, the same cloth is used and released at constant height. In each attempt, the timings for the folded cloth and unfolded cloth to fall to the ground are recorded. A repeated attempt is done before averaging the values to ensure reliability of the results, since human error is significant due to the short timings for each attempt. The air resistance, also known as drag force, is calculated by multiplying the coefficient, the density, velocity squared, and reference area together before dividing the answer by 2. In fluid dynamics, the drag coefficient is a dimensionless quantity that is used to quantify the drag or resistance of an object in a fluid environment such as air or water. The coefficient contains all the complex dependencies and is usually determined experimentally. A lower drag coefficient indicates that the object will have less drag. In the video, the folded cloth fell faster, as it has less surface area for collision with air particles. The drag coefficient for the folded cloth is low, and there is less drag force present. Therefore, the weight of the cloth outweighs the small air resistance, and less time is taken for the folded cloth to fall. On the other hand, the unfolded cloth fell slower, as it has more surface area for collision with air particles. The drag coefficient for the unfolded cloth is high, and there is more drag force present. Therefore, the weight of the cloth has the same magnitude as the higher air resistance, and more time is taken for the unfolded cloth to fall. To summarize, we have covered the concepts and applications of torque and air resistance. For torque, recall that it is dependent on force and its perpendicular distance from the pivot. It is present in daily activities such as opening our doors. For air resistance, recall that it is dependent on the drag coefficient. Drag can be very useful in activities such as parachuting and can be investigated further in our daily lives. In addition, the topics of moments and forces tie in to the larger concept of equilibrium, as the balance of torque about a pivot is related to rotational equilibrium, while the balancing of forces is part of translational equilibrium. The application of equilibrium can be seen in the launching of a multi-stage rocket and the use of gravity assist on spacecrafts to save fuels. This is because of the principle of conservation of momentum, where the sum of initial momentum is equal to the sum of the final momentum in the absence of net external forces acting on the system. Hence, the study of moments and forces allows us to gain further insights into the study of equilibrium. Thank you for your kind attention.